All right, today we're going to do chapter 5, nuclear chemistry. There's no homework up yet, but there will be some up in the next day or two. There will not be a quiz for chapter 5, there will be homework, okay? Short chapter, we're going to cover the whole thing today, okay? And then when we finish chapter 5, so like next Monday, the next time we meet, we'll start on chapter 11 and we'll start on organic chemistry. And like I don't know if I told you guys, so who in here is glad we're finished with conversions now? We have no more conversions to do. Well, except for the tests, right? We're not going to cover any new conversions. How's that? Is that good?
Yes.
Tired of doing conversions?
Yes.
No, not really.
They're easy once you figure them out. Once you figure out like the puzzle, right? How they fit together, not too bad. Most of them kind of got the idea. So yeah, so we're pretty much done with conversions. So anyway, we are all students. You know I'm a student, right? Constantly learning. None of us have been elected to be president of the United States yet, right? Anybody in here been elected president of the U.S.? So we have no deities and nobody's been elected president. So when you pronounce that word, it is nuclear, not nuclear. Does anybody know that reference? George Bush used to say nuclear all the time. And every time I heard him on the radio say that, it would drive me nuts. Because it is there's only one U in that word. It is nuclear, not nuclear.
Well, we also have someone in the office that can spell potato.
So up at Sharon Harris, they have a nuclear reactor, not a nuclear reactor. Okay?
Gotcha.
So what do you think of when you hear about radiation?
X-rays.
X-rays are a form of ionizing radiation. Yeah?
Sunburn.
Yeah, it's not exactly what we're talking about, but sort of. Do you think of fear? Are you scared when you hear radioactivity? You hear that word, what does it do to you? Makes you go, uh-oh, right? Better leave that alone, right? And for some radioactivity, that is very true. You should be very cautious with it. But hopefully one of the things you'll see today is not all radioactivity is bad. It's got lots of medical uses. And some of it, all you have to do is sit it on the table and step away from it and you're fine, okay? So we're going to talk about the different types of radioactivity, the different types of radiation that come from it, and then some of the different uses for radioactivity and nuclear chemistry. So up to this point, everything we've really talked about as far as chemistry and chemical reactions, bless you, has been dealing really with electrons, right? Electrons where almost all chemistry occurs. There's a small part of the chemical field that talks about nuclear chemistry, dealing with which part of the atom? The nucleus. Okay, so you guys should all remember this right here, right? Here we have iodine 131. The 131 is the mass number, right? Where do you find the mass number on the periodic table? It's not on the periodic table, is it? Because if you look at iodine, the atomic mass is nowhere near 131. It's like 127 or something. I can't remember. Okay. Now 53 is the atomic number of iodine. Every atom of iodine has 53 protons, but they have varying numbers of neutrons. If you go and Google isotope chart, you'll find that there's literally over 1,000 isotopes, which is barely over 100 elements, right? So that means on average, there's about 10 isotopes per element. Most of those isotopes are radioactive. About 900 are radioactive. Only 100 are stable. So most isotopes of elements are radioactive. And what does that mean? It means that the nucleus decays and gives off a certain type of particle or energy. Okay? We're going to go over these different types of particles and energies, okay? This radioactive isotope is unstable. The nucleus somehow does something, it rearranges itself and gives something off to make itself more stable. Kind of like the atom giving off an electron or gaining an electron, right? So the electron configuration would be more stable. Well, the nucleus does the same thing, okay? And when it does that, it emits radiation. Some of the radiation has mass, some does not. We're going to talk about alpha particles, beta particles, positrons, and gamma ray emissions, okay? We're going to go through each one of these. So the first one. Oh, my bad. So when radiation is emitted, a radioisotope can change the number of protons that it has, and it may be converted to another element. What is key though? The mass cannot change. The total amount of mass has to always remain constant. Why? Why does the total amount of mass have to always remain constant? What did we say earlier? Nobody's been elected president and nobody is a deity. So what does it mean that you're not a deity? You can't create or destroy matter, mass. You can't create or destroy mass. So products and reactants have to have the same amount of mass. Now what's a little bit different here than the other reactions we've done before is you can change the elements, but the total amount of mass has to stay the same, okay? So keep that in mind while we do this. So, how do we say the names of these isotopes? This is that same iodine that was on there before. We would say that this is iodine 131. And everybody would know which isotope you're talking about because every atom of iodine has 53 protons, and it can be written as either the whole name -131 or just the symbol -131. Okay? So, here are some other common isotopes that you may hear about. Stable isotopes, magnesium-24 or iodine-127. There are no stable isotopes of uranium. All uranium is radioactive. There are lots of radioactive isotopes of uranium. They only have 2 listed here, but there's also uranium-234 and uranium-232 that are also radioactive, okay? Iodine has a couple of radioactive ones and magnesium has a couple. So, first 2 types of particles, alpha particles. Alpha particles are like the big truck of particles. They have a mass of 4 and they contain 2 protons and 2 neutrons. They are very slow moving because they are very big, okay? It is identical to a helium nucleus. Charge of +2, okay? Beta particles. Beta particles are an electron, but they have very high energy, okay? So think about it. If I get rid of an electron, that's negative charge, there must be a positive charge someplace else. And beta particles result when a neutron falls apart and makes a proton and an electron. Now, who knows about the Big Bang? Not just the TV show, but what was the Big Bang?
When the world was created, it was a big bang.
When the world was created, when the universe was created, there was a Big Bang. And at the beginning, the only types of particles there were neutrons. Neutrons fell apart. And when neutrons fall apart, they make protons and electrons. Okay? Why do they do that? They just do. That's all you gotta know. Some neutrons fall apart. They're not stable. We all have people we know like that, right? They're just not stable. They just fall apart. You look at them, they go boom, fall apart. So if it's going to make a proton, it must also make an electron. Why? Why does it also have to give an electron if it makes a proton? Because it has to be neutral, right? A neutron is neutral, no charge. So if it makes a positive charge, it also has to make a negative charge. Remember, we talked about positive and negatives. Can't have one without the other. So if you make a positive, you also have to make a negative. So beta particles are high energy electrons that are ejected from the nucleus when a neutron becomes a proton. Positrons. Positrons are this really weird thing that when I first heard about them, I'm like, what the heck is that? It is a positively charged electron. And you're like, that should go, what? Yeah, see? What do you mean positively charged electron? The definition of electron is what?
Electron.
that it's negative, right? Well, sorry. This throws a wrench in it, right? It is said to be a form of antimatter. So if you're into Star Trek and all that stuff, you know about antimatter, okay? Black holes, all that kind of stuff, right? Yeah. So, a positron is a positive electron, and it's formed when a proton decays and makes a neutron. Okay? So before we had neutrons making protons, now we have protons making neutrons. It happens. Okay? The gamma rays is the last type. Gamma rays are just energy. And gamma rays are a result when the protons and neutrons in a nucleus rearrange themselves and they just give off energy. And they can give off gamma rays. So, this table just summarizes the different types of radioactivity or different particles. There's alpha particles, which have a mass of 4, beta particles, which are high energy electrons, positrons are positively charged electrons, gamma rays are just energy, okay? Then protons and neutrons. So, I'm not going to worry about this so much.